Hello, my name is Matthew DeSaulnier, and I did my term paper on the simulation of state feedback system simulation of a state feedback system used to control a brushless motor-driven bike. So first, some motivations. A lot of work has been done recently in automating vehicles. However, a lot of those vehicles have been cars, trucks, and larger forms of transit. However, it's been projected that the micromobilities market, that is to say, small electric bikes, electric scooters, regular bikes, that market is projected to grow from around 7 billion, where it's at right now, to 200 billion in the US alone by 2030. So this is a really good time to get into that market and start applying some of the things that are already applied to autonomous vehicles onto micro-mobility type of vehicles. What we're going to go over is the modeling of a motor and bike dynamics, converting that dynamic model into state space form, and then we're going to verify our model and then do a little bit of control system design and then talk about the different implementations and how those would be taken into consideration in a real world scenario. So first, for the model derivation of the motor, we do a simple KVL for the electrical circuit, and this is going to be the mass, the actual physical parts of the motor that we'll model. So as far as the KVL goes, we have our input voltage, some constant times V, plus current through a resistor times the resistor to get the voltage over the resistor, plus voltage over an inductor, which is the inductance, times the rate of the current. And then for the voltage over the motor, we have some constant times the rotational velocity of the motor. And this constant will just convert the units so that we can look at this voltage in terms of how quickly the motor is spinning. And then on the motor end of things, we have the inertia of the motor plus the friction plus the actual load force equals the amount of force we're driving into the motor through our input signal, I, times some constant. So it's important to think of this equation as this is what we're inputting, this is what's actually getting driven, and these are taking energy away from what we're inputting. Now for the bike kinematics, we saw that TL was actually what was being input, so this is actually the force on the load, which in our case is the bike from the motor's perspective, I should say, that's the force on the load. So epsilon M and G actually serve to convert this TL all the way to the wheel through gear reductions. So epsilon M is the reduction from the motor gears onto the cassettes of the bike, and epsilon G is the reduction of the front cassettes to the back cassettes of the bike. TR are our resistive forces that are acted upon the tire. B omega W are the friction forces on the wheel, and JB omega dot W are the inertial forces of the tire. So we're going to combine these models together by using this TL term. So all you have to do, divide everything by the gear reduction ratios, you get TL by itself, and then we're going to go back to our motor equations, and by plugging them into the second inertial equation of the motor, we find these. And this is just the first equation of the motor rewritten when we originally did the KVL. So same things, we've just organized it in terms of states now. One important thing to see, so we have I, or DI, we have I, we have omega, we have D omega, another omega, things are looking good so far, and then we have TR. TR is a constant term being added on to these differential equations. Normally that would cause some issues, but we're going to circumvent that by just making it a state. So we know it's going to be constant, and it's added on to our dynamic equations, which kind of messes up our matrices. So we just make it a state, And because it's constant, that state is 0 all the time. So we have the rate of current, rate of the motor velocity, and the resistive forces on the tire as our states, and we have our A, B, C, and D equations using all the variables we discussed before. Important to note, this just gives you the output of the actual wheel. So we converted the motor velocity, omega m, to the wheel velocity using some standard unit conversions, and also, most importantly, the cassette epsilons for gear reductions. So there's already a study done on modeling a bike that was powered by electricity and a human. However, they purely did their tests on modeling the electrical aspects of that, and they were found to be true. So the bottom graphs are the outside studies, and you can see kind of they're actually labeled. So what we're verifying our graphs against are the simulated curves that they have here. And the general idea is if we can verify our simulations against their simulations, and their simulations were verified against experimental data, then our simulations should be good enough. So in this case, first looking at the current, we see it goes up to around 1. This was 2 tests, one with 0.8 volt input and one with 0.6 volt input. So for 0.8 volt input, it goes to around 1, and 0.6, it goes a little under 1. And we look at their current, and you can see this dashed line here. It goes up to around the same peak in both cases, and it also has the same characteristic, goes up almost like a cliff face, very rapid drop to a steady state response. And the same analysis for the wheel velocity and RPMs can be applied to theirs. The curves are very similar, and the output maxes are also very similar. So now on to the controller pole placement. Since we were using state feedback, we chose some poles to see how the system would respond. And to do these simulations, we just used initial conditions and watched the response back down to a 0 steady state. These were actually the original poles of the system, so this is the natural response with no control signal. And you can see that here, our control signal amplitude is in the 10 to the negative 13 range, so that's almost nothing. You're not using any energy, and that's because you don't have to compensate for anything in the system. So we can see naturally the system current goes down to about negative 100, and then has a little bit of an overshoot and steadies out. The radians per second of the motor also has some overshoot, and everything finishes responding, settles down around 20 milliseconds. So this next controller is much more snappy and aggressive. We move the pole out onto the left-hand plane by 1,000, and you can see the differences. Our controller goes down to about negative 27 volts now, which is much greater. This may or may not work depending on some controllers or motors that are being driven. However, the response is much snappier now. It's actually half of what it used to be, so the settling time is now 10 milliseconds as opposed to 20. But the kind of trade-off here is that the current now almost goes down to negative 200 amps for this much quicker response time. The next pole has no imaginary components and is moved over only 100 further onto the left half plane. You can see our control signal goes up to about 1.1 volts and then settles down. And our system responses are still, they're a little bit faster, still close to about 20 milliseconds, maybe 18 milliseconds. But the current draw through the motor is actually smaller here than the completely uncompensated system. So our controller is in effect saving life on the motor in a way due to it drawing less current to get the same job done. Actually, in the same speed, a little bit faster. And there is no overshoot in either case. And as far as the wheel goes, we have just a little bit faster response time than the original. So some discussion. The controllers themselves, neither is objectively bad. It always matters how, where, and why are you implementing this system. If you don't need a snappy response or something that can settle down within 10 milliseconds, then you don't need the second controller. Or if, let's say your motor driver can't actually accept 27 volts or negative 27 volts, then there's no way you can use the second motor controller, even though theoretically it might be completely superior. Another thing is that if you actually look at the energy of the input signals, the second controller consumed something on the order of 100 times as much energy in the actual voltage signal being sent to the motor. So that's another thing, is that although it was a better controller, once you go to implement it, there's a lot of issues that come up with how much current you're drawing, how much energy you're inputting into it, and also, can your electronics handle not only the rate of the change, but also the magnitude of the change of these states. So generally speaking, the third controller would be the best, most ideal system. Obviously, it actually reduced current from a no controller state, so that's good. You're reducing the energy in the system. The input control signal only went up to about 1 volt, which is super compatible with almost every single motor controller. And there's actually probably some leeway for a more aggressive controller, and that could be part of some future work to be done. Thank you.